Okay, say hello to the people watching this. Fine, they don't like you. Yeah? Tell them to watch the video, slackers. Oh, they better. They weren't here Friday. There are a couple videos out there. I'll post them today, but again, it's practicing the problems that we just did, so it's several pages in your packet. So strong acids and strong bases are what we're looking at here, if I can get this to the right size here. So when we talk about strong acids, the big thing is they ionize completely. So when we look at these, when we try to do, the equilibrium stuff, really we don't even have to. So, and here's the tricky part, and this is one that you'll see, I've seen a couple of times on there, where they talk about hydrochloric acid, and they'll ask you what's the concentration of the hydrogen ion concentration. Well, if you have 0.1 molar hydrochloric acid, it's going to ionize completely. So the concentration of the hydrogen ion is 0.1 molar, right? It completely ionizes. Remember, that's not why we need the equilibrium expression. It's not the strong acids and the strong bases that cause us to need to talk about reversible reactions. It's the weak ones. The weak ones where the reaction of them splitting into two ions doesn't go to completion. So when we talk about strong acids and strong bases, they ionize completely in solution. And then I'm going to use a little bit different phraseology over here, because with an acid, it's a covalent compound. It forms ions where ions are not present. With the bases, these are ionic compounds. They don't ionize, they're already ions. These dissociate completely. Dissociate means they split into their ions. Okay, so strong acids ionize completely. Again, the reason I'm using the word ions, because ionize means they made ions where there weren't any. HCl, covalent compound, no ions anywhere. NaOH, that's an ionic compound, a metal and a nonmetal. So the strong acids ionize completely, the strong bases dissociate completely. No matter what, they're splitting into their ions. Totally and completely, where it's not a reversible reaction. So typically when we write it, we would write it this way. If I could write it correctly, HCl would be written H plus Cl minus. Just one arrow in the direction here. If we talk about sodium hydroxide, again, these are the two classics. It's just one arrow. We don't put the equilibrium arrow. Examples of this, you have them on I gave you a sheet in your notes, so you should know those. Strong acids and bases are both strong electrolytes. This is actually how they came up with the name. Again, it doesn't mean that it won't eat your face off, okay? When they say weak acids and bases, it means that they don't conduct electricity very well. So when they say strong acids and bases, they conduct electricity really well. Somebody asked about battery acid, H2SO4. That is a strong acid. It's a great conductor. Yes, that's why we use it in batteries. Okay, weak acids and bases, and I'm not going to put them in all caps because they're weak. It's the little things that count. Weak acids and bases. Weak acids and bases don't dissociate or ionize completely. This is where we need the equilibrium expression. So that's why we have these equilibrium expressions. If they ionize completely, it's really, really simple to find the concentration of the two individual pieces. But in this case, since they're going forwards and backwards, and again, I'm going to use the acetic acid over here, so HC2H3O2. Now we have the double arrow, where we've got the hydrogen ion and the acetate ion. Or if you put it in the way of the organic, that's the same thing. This is the same thing. A lot of times when they write the weak bases, they will write in the hydrogen ion. I'm sorry, they'll write in the water, sorry. Trying to break stuff there. So in this case, what we have is something where we are not letting it ionize completely. So if you flip in your packet, find that chart that has weak acids and weak bases, or strong acids and strong bases, would you? I don't remember what page it is. Did you guys mark it? No, because I told you to, so you didn't do that? Page 10. So if I look at my bases here, let's say I put magnesium hydroxide is considered a weak base. So I would put my double arrow, and I'd have the magnesium ion plus the hydroxide ion. And again, that's when I need that double arrow. It's a weak base. It does not dissociate completely. So now what we're stuck with is we have to say, okay, fine, now I have to figure out, well, what's my concentration of the magnesium ion in solution, and my concentration of hydroxide ion will be twice that, right? So for every 1 mole of magnesium ion, I have 2 moles of hydroxide ion. But it's not, if I have 0.1 molar magnesium hydroxide, I'm not going to have 0.1 molar of this and 0.2 molar of that. It's not going to be that, because it's not going to ionize or dissociate completely. Yes? That's the whole thing about the equilibrium expressions. It's the fact that these reactions don't go to completion. Even though we say this isn't a chemical reaction, this is just, do I need small too, sorry about that. Okay, so again, it's all about the fact that it's not going to completion, so you have to figure out what's going on here. All right, Because of this, we have to calculate the concentration. So we have to use this piece right here. We have to use the equilibrium expression to do that. You know how when we had KSP, we had products over reactants, right? We're doing the same basic thing here. It's just that our reactants are not solids necessarily. In this case, since this is a base, it's going to be an aqueous form, so everything would be aqueous. So when we did KSP, it was did I say reactants over products? It should be products over reactants. We had products over reactants, but our reactants were all solid, so we crossed it off, right? In this case, you're not crossing it off because everything's going to be aqueous. Yeah, this acetic acid vinegar is aqueous. The magnesium hydroxide, it'll dissolve in water to a certain degree, and it'll be aqueous. So we have that there. It's just that we can't. So when we write our expression, it's going to be that. So when we have this, let's see. Some of this stuff I don't need to write on here. So I'm going to write this in the terminology that they're writing this on your green pages for your pages for your test. I got to shrink this down some people. I can't get it all on here. So you're going to have to, I'll try and write bigger. So I'm going to use the terminology they do. So take out your green pages, yellow pages, whatever color pages you have. KSP would have been over here, yeah. So this was KSP. Let me write it darker. Yeah. So with KSP, we didn't put the reactants on there because they were solid. When you take out your sheet here, you'll notice that when they start talking about Ka and Kb, they throw in all these letters at you. So that's what I'm going to explain it in terms of. So let's talk about some of these. So the capital H, if you'll keep those pages handy, you can look at this. So capital HA equals the hydrogen ion and the anion of an acid. The B is going to be the base. It's undissociated. So it's just the whole base. So they can talk about an acid, HA, and it's going to separate into H plus and the anion, and I'm going to put my arrow both ways. And then we can talk about the base, and it's going to separate. Remember bases acceptors, right? Yes? So that base is going to accept an ion, the hydrogen ion, and it's going to spit out the hydroxide ion that it has. Another way to look at this is if you write them with water, like I'm going to show the water. A lot of times it's easiest to show the base with the water included because that's where you can see the hydroxide ion. So if I show this same thing, then I've got the base and I'm going to include water. So we just put it in more water, right? It's in water. So now what happens is it accepts this hydrogen ion because this acts like an acid. So we have HB, and it went from a neutral state to a positive one, and then it's got the hydroxide ion left over. So a lot of times when I look at this stuff, I like to incorporate the water in everything. I can do it in everything, or for me, I just like to do it with the bases. But it's up to you. Does it make more sense for you to include the water in it? But remember, water is a pure liquid, so you're never going to use it in the equilibrium expression. If I did this over here, I would have HA, and I'm going to leave it as H2O. Acids, donors. So it's going to donate that hydrogen ion here, so I get H3O plus, and the anion is all by itself and it's a negative charge. These are the same. These are the exact same. One incorporates water with it where you can actually see the water inside there. The other one doesn't. And it's really a preference on your part. Which makes more sense to you? On which ones you choose, which ones, how you choose to write it. Just remember that when you have the equilibrium expressions, water's a pure liquid. It's never going to be incorporated in that. So Ka is going to be products over reactants. So we have the anion concentration times the hydrogen ion concentration over, not water, because water's not in there, HA. That's how they came up with that equation right here. So notice on the AP test, instead of using the hydronium ion H3O+, they just used the hydrogen ion. You know, he was talking about it's truly more accurate to use H3O+ ion, but on your chart here, they're not using that. And that's kind of old school. Over here for KB, same thing, products over reactants. So we have the hydroxide ion concentration, and we have the base that's just accepted its hydrogen ion, its proton, and then it's over the base, the concentration of the base. So everything is included there. Because the base originally started out, you dissolved it in water. Again, typically, acids and bases, they're not technically considered acids unless they're dissolved in water. Same with the bases, it's usually got to be dissolved in water there. Okay. The next thing that we come to is what happens then, because it's not all about the strong ones. It's not all about the strong ones. It's all about the weak acids and bases. It's all about the weaker ones because they don't dissociate completely. And it can be just weak bonded to weak, or since you can have a strong acid and a weak base, you could do that too. But whenever they throw in the weak stuff to you, that's where you have to start figuring out, well, what do I have to calculate? And one of the big things they like to talk about are weak acids and weak bases. So if they combine a weak acid plus a weak base, you're going to get, one of your products is going to be what? Always. You combine an acid and a base, one of the products is always water. Always water. Always. It's always going to be water and some kind of salt. In this case, though, they're going to ask you what's the pH of the solution. If we have a strong acid and a strong base, it's pretty easy. In most cases, it'll be neutral. If we have a weak acid and a weak base, now we have to figure out the concentrations of both and figure out what the pH is going to be. So the salt and the water don't necessarily have to be neutral. Yes? And we talked about that before. If we have hydrochloric acid and sodium hydroxide, well, yeah, they can be neutral if we have the same molarity. But again, you throw in hydrochloric acid, a strong acid, with a weak base like magnesium hydroxide, you're not going to get a neutral solution. The strong is going to overpower. You're going to have an acidic solution. You could test the pH and it's going to show up acidic. Yeah? So this is one of the things that they like to ask you about. Okay, next page. And we're going to practice on those two. So the next thing we're going to look at is titration. Okay, so titration is when you have some type of burette. I'm going to draw a lovely picture over here. Okay, and you're going to drop stuff down. So here is where you have the unknown. And it's not that you don't know what chemical it is, it's unknown concentration. There's your unknown concentration. Here, this could be an acid or a base. We don't. It's just something that it's going to be an acid or a base of some kind. Whatever chemical it is, that's your unknown. Here, it's going to be opposite. If it's a base that's in here, you're going to have an acid. If it's an acid that's down here that you don't know the concentration, is going to be a base up here. In the flask down here, not only are you going to have the unknown, you're going to have some type of indicator. Something that changes color. Because if you put an acid and a base together, it doesn't look like much at all. The temperature looks clear. You start out with it looking like water, you end up with it looking like water. It doesn't look like anything. So you really have to have those indicators in there to show that something's happening. I mean, other than the changing of the temperature, there's not a whole lot that looks like it's going on. I suppose if you tasted it before and after, you would taste something different, but yeah, that would be bad. So that's why we use those indicators. The indicators are really incredibly useful because it tells us what's happening. If we choose the right indicator, then we're going to know pretty close to when we get equal numbers of moles. Because when we get equal numbers of moles, that's where the color changes. But you have to get the right indicator. So a lot of times you can do some calculations ahead of time and you can kind of figure out, well, what's my pH going to be and blah, blah, blah. So you can do some calculations and then you go in ahead of time so you know, now I did this on paper. Now I'm going to go in the lab and figure out, well, what indicator should I use? So when you did your lab paper, you noticed that indicators change at different pHs. You'd want to pick the best indicator for the job. I like universal indicator because it's one chemical and you can kind of, okay, here's my endpoint, that'll work. The only problem is that you have to know which color you're looking for. So if you're doing titrations, it's actually smarter not to use universal indicator, but to use a very specific one that you know is going to change it. Oh, well, it's probably going to be around 9, a pH of 9, so let's get one that changes around there. Using indicators is not incredibly precise. It gives you a pretty good idea, but it's not perfect because you're waiting for something to visually happen there. What's best is if you use a pH meter. Yes, if you use the pH meter, you can use the indicator also, so you can see a visual thing that's going on, but really, if you read the pH, you can see it that way too. Okay, so here when we talk about titration, we're combining a known combining a known concentration of some acid or base. So you might know the concentration of the acid. So you're combining a known concentration of acid or base with an unknown concentration. Acid or base, or I'm going to put this backwards, base, acid. So one of these is, let's say you've got an unknown concentration base. You know what the chemical is, you don't know the concentration. Then you're going to try and figure that out. And to determine, the whole purpose is to determine the unknown concentration. That's the key. Your purpose is, I want to figure out what the concentration of that acid is, or what the concentration of that base is. That's why you do titrations. Using an indicator, that's a big part. Either one, whichever one you have. Whatever chemical you have, the acid or the base, whichever one it is that you don't know the concentration of, that's what you're trying to figure out. So you're going to use something that you do know, and you're going to chemically combine them until you get equal moles of them, so you can figure out, well, if they're equal moles, then I can figure out, well, what the concentration is. Okay, so this indicator, again, that's important that you choose the right one, changes color at a specific pH. Oh my gosh. Okay, so here's the kicker. You know the identity of one of them. You know the, okay, so let me say that again. You know the identity of both. And I had someone really get confused about this. You know what they are. You know, oh, hey, that's sodium hydroxide, or that's hydrochloric acid, or that's magnesium hydroxide, or whatever. So you know the identity of both, you just don't know the concentration of both. So one of them you don't know the concentration of. Okay, write one more thing down and then we can take a break here. This will be an acid-base reaction, aka a neutralization reaction. I don't know what they'll refer to it as on your test. They're the exact same thing. So an acid-base reaction is a neutralization reaction. Once you have that down, go take a break.